Hi, I'm Sanja. Nice to be here. Can you hear me? Kind of. So most of the stuff I'm going to be presenting is work in progress, not even published yet. So if you have any questions, suggestions, feel free to stop me. All right, so I just wanted to start by announcing that we just opened the Vector Institute, which is a new research institute we founded in Toronto, just across basically the lab. It's basically going to be focused on deep learning, and it's just pure research based. It's mainly government funded, and we're planning to hire 20 principal research scientists who can hire students through U of T, so it's a pretty good deal, and some of them are actually paid by the institute. So, just apply. So this is basically the founders team, including Jeff Hinton in the middle, and I'll let you find the banker in the group. But it's basically the full machine learning group in Toronto. All right, so I'm going to mainly talk about captioning today, since it's kind of related to the theme of the workshop. And just to review a little bit of captioning stuff, right? So basically the idea is that, you have an image. Hello. I'm too tall. All right. I can't pull it out, so. It's going to be an echo. Hello. Hello? Can you hear me? It's better? Okay. All right, so the goal of captioning is you have an image, and now you want to kind of go to a joint space together with captions from which you can either decode a caption or retrieve images. But basically the point is you want to kind of find a joint space between two different modalities, right? So the common approach has been, you embed your image, and then you have an RNN that basically decodes this caption, right? But there are kind of problems with the types of approaches, right? Let's say that you have this image. This would be some ground truth. I don't know, a black cat sitting by the window. And then maybe the generator right now thinks that this is actually a black, without an A, black cat sitting by the window, right? So basically, this is a problem, right? Because if you train this with a normal metrics, which is like cross entropy at each time step, which is how people are training it now, like the generated sentence is completely wrong under that loss function, just because of this one word switch, right? And now, let alone if you kind of jumble these things, right? So the question is, can you actually directly optimize caption generators for your desired metrics, like Blue Score, or Meteor, or Cider, or things like that, right? Can you? Yes, so yeah, but there's some problem, right? So that's loss function is not differentiable. You only get the loss, right? How well you're doing once you generate a full caption, which means that you need to actually sample from your model, okay? And there are basically ways to actually still do that, right, using reinforcement learning. And we've seen a couple of talks, I think, at the conference, and Dave and Drew also have some nice work on that. Right? But basically, the idea is that now you're treating the captioning system as a reinforcement learning task, so as an agent that interacts with images and words. Okay? So it's going to be producing words at each time step, and you're treating the selection of a word as an action. Okay? So basically, selecting a word over here, you can think of it as selecting an action, and your caption generator is following a policy, which is basically your neural net, your neural decoder. Okay? And basically, in the end, once you generate the full caption, you get your reward. Because you have your ground truth caption, you can compute now all your metrics. Okay? And basically, now you can do something like policy gradient optimization, right? Because you're just trying to improve your policy, which means that you have your typical loss function, and you want to maximize the expected reward, right? And the reward in this case would be your desired metrics. So there's some fancy math from the 90s that basically allows you to compute gradients here. It's super simple, actually, which is basically this expected, and you have some gradient of the log times the reward function. It almost looks like cross entropy, right? It's just that now you have this, this probability basically multiplied by the reward instead of 1, which is the cross entropy case. Okay, so it's super simple to actually optimize for this. And then there's ways to actually improve that by adding baseline and so on, and I'll not talk about that here. Okay, so this is a paper I think was presented at CVPR here, not ours, Renier et al. That basically shows that now that you're trying to optimize for this matrix, you really get much better, like huge improvements in the actual performance for this matrix. Okay, but the problem here was that you're still relying on this. So this reward, computed reward, is relying on standard metrics like blue score and all these things, right? Which maybe we can all agree it's maybe not the best metrics to optimize for. Okay, so we're going to do a little bit different here. So we're going to use a GAN model to actually train the generator as well as the reward function. Okay, and the idea is going to be the following. So you have your typical captioning system, right, where you have an image, you embed it, and then you have an LSTM that's basically going to be generating words. But you're also inputting this noise variable, right, this latent variable that's kind of telling you different types of topics you might be talking about when you're presented with this image. Okay, so the input to the LSTM is the embedding of the image as well as this, noise vector, which just follows a normal distribution or something like that. Okay, so this is the generator. Right? And now you can also add a discriminator, which is going to read your image, take the generated caption, and is going to be deciding whether this caption looks good or not, given the image. Okay, so it's basically judging the pair, whether the caption looks good as well as whether it's relevant to the image. Okay, and what it's going to try to decide is whether this caption looks fake or not, human written or automatically generated. Okay? And now you can basically do your standard GAN trick, right, where this the generator and evaluator are kind of playing this game, right? The generator tries to be as good as possible, right, to fool the evaluator, and the evaluator tries to be as good as possible to discriminate between them, right? So now you can think of the discriminator to actually send a reward, which is how well it's classifying human versus fake to the loss function. Okay? And you can do fancy tricks, so now you can have improvements in all the metrics, whatever. But what I wanted to show here is that as a side result over here, you're actually also training a better evaluation function, right? Because if you look at these different rows and different metrics, for almost all metrics, the human is worse than the captioner, right? If you take blue, if you take, rouge, even for spice, right? The human is the worst, right? Which probably we can agree that maybe it's not the correct thing. Whereas for the evaluator, which is the last row, it actually puts the human as the ground truth, so it's the best metric. So it looks like maybe it's a better way to measure how good sentences are. So it's kind of nice because you get it for free, right? You get the generator and the evaluator as part of just optimizing this one thing. Okay, and now you can show this to humans to have maybe a little bit better evaluation. So basically, you're showing human captions, one from the GAN model, one from the maximum likelihood, which is just following the standard loss, and then you need to choose which one is better. Okay, so you can see in the first thing is that the GAN always wins by quite a lot. And even when presented with human captions, it actually wins a few times. And it's doing much better if you're just showing the maximum likelihood captions. So it improves actually by quite a bit. These are just some results. And now basically the Z variable allows you to actually achieve variability in your captions, right? Because you can sample different samples and kind of learns different topics for each image. So here, different rows are going to be kind of different samples from the model. And if you read them, they actually look a little bit more different. You can do it also in paragraphs, right? So this method is not tied to a particular LSTM. You can just have a hierarchical LSTM, and it still works. So it can generate paragraphs. Yeah, and now let's switch a little bit gears. So now let's take this image. And this is actually a state-of-the-art caption as a result of state-of-the-art captioner. Okay? So if you read this sentence, it has all the keywords, looks good, but it's totally wrong, right? It doesn't make any sense. A computer sitting on top of a desk on a monitor, right? It's bad, right? But even though maybe all the blue metrics would actually say it's good, okay? So what we're going to do here is we're going to try to put a human in the loop to help learn this agent, right? We're talking about the reinforcement learning agent, okay? So we have our machine, our agent, that is basically taking an image and generating a caption, okay? And now we want to put a human teacher that's going to be observing what this guy, what this agent is generating, and it's going to be able to provide feedback, okay? And this feedback is not just going to be a new caption, right, which is what people are typically doing. It's just going to provide some feedback of what is wrong and what is correct, right? Which is basically how humans learn, right? You typically, say something, and then your mom says, well, here is a mistake, right? Not just going to tell you, OK, this is how you should do, unless it's a bad mom. So, all right? So basically, this is going to be the setting. And you can do this in a continuous fashion, right, where this agent is going to explore the world, try to caption everything, and then we have a way to just, with natural language, influence what is producing. Okay? And the main challenge here is going to be put this natural language in the reinforcement learning framework, right? So use it to actually provide the rewards to the agent. Okay? There's surprisingly very little work on that. Okay, so this is kind of the overview of what we're going to do. So one thing here is that if you notice the feedback, and just in general, if you think about it, people typically provide feedback for a single word or a single phrase at a time, right? They will not put too much information on you. They're going to focus on one mistake at a time, okay? And so that's why we decided that, well, let's just, output phrases if that's the thing that people are going to help us with anyway. Okay? So we're first going to just, a very simple phrase-based captioning model, which is basically hierarchical RNN. And you have now one RNN, the higher level RNN, that's basically going to decide what each phrase, the topic of each phrase, essentially. Right? So you should talk about the object, you should talk about the action, and so on. So this is just a hidden state kind of captures that topic. Okay? And given that hidden state, then you have a word RNN that just produces that phrase. So you kind of decouple this long caption into short snippets. And so it's much easier for the word RNN to actually produce this. Okay? You have some label, and you also add the image. Just at each time step, you're going to be looking at the image the standard way, using attention, and some way of encoding what you have produced and putting to the next time step. And this is actually important so that the next time step knows what you have previously produced. Okay? This is just one result. You have an image, and below is a caption. And each time you see a bracket, that's basically a phrase. Okay? So you have different phrases separated by brackets. Okay? And for each one, we also produce a label, which tells you whether it's a noun phrase, verb phrase, preposition, and so on, and a heat map. All right, so now we actually want to put a human in the loop in this, right? Yeah, let me just tell you what we did. So basically, we took a snapshot of the model, which was just the model trained with maximum likelihood. Okay, so this model is pretty good, but still going to be making a lot of mistakes. Okay, and now we're going to show those captions and images to annotators, to teachers, okay, to mechanical Turkers. There's debate whether they're teachers, but let's try to use them. It's a very simple task. Everyone can see whether it's a reasonable caption they're producing. Okay, so in the top, they're going to be seeing what the machine currently thinks this image is about, so the produced caption. And then what they're going to be producing is some feedback. Okay, so the first form of information is just in natural language. So in this case, there is a dog on a sidewalk and not a cat. Okay? And then we're also producing a bunch of other information that we're going to just be using to train some network later. Okay? But in principle, we should just be using the sentences. Okay? And this information is going to be like, is it the wrong object, an action, or any other type of mistake. And then they're going to also mark where exactly you made a mistake for this particular feedback, and then correct it. Okay, so these are all these types of information that you're getting, right? So you're also getting basically a corrected caption in the end. So this was the actual interface, right? So they input all this information, and we asked them to talk about one mistake at a time, okay? And we only paid for fixing one mistake, but there was a hidden button which you could click and say, okay, I'm willing to do one more mistake if there were more mistakes in the captions. All right, and what happened is that we had one job, we paid 15 cents, and they needed to correct all the mistakes, so fill out all this information. No one was taking the job. Then we put 7 cents, and we said only do one, but do more if you're willing. And it was going very fast, and everyone was correcting everything. So people like to work for free, basically. Not everyone, but most of them. Okay, so this is some statistics that you can get. So on the left side is some statistics of the types of, the quality of captions after the maximum likelihood training. Okay, so we had 5 categories: perfect, acceptable, grammar errors, and then just semantic errors, either minor, maybe a wrong attribute or something, or major error, like real complete misunderstanding of what's in the image. Okay. So even after maximum likelihood, there's quite a lot of good captions, but you can see there's also a lot of mistakes, right? And maybe these current metrics are actually not taking these mistakes into account properly. Okay. This is after evaluation. Again, this is using this human correction. You can see that these captions, after they have fixed all these mistakes, mostly perfect and acceptable, there's also some errors. So not everyone fixed all the errors. All right, so this is some more statistics. I have to say we only use 9,000 images and captions here, so not the full COCA. Otherwise, we would go bankrupt. And these are just some statistics, right? So the majority of error is that some words should be replaced, meaning that the majority of errors is misnaming some object or an action. Okay, so that's almost 3,000 cases are like that. Okay, and then there's also some other statistics, like something is missing. Maybe you are missing a salient object or something, and people complain. Or that something should be removed. For example, you're regenerating the same phrase, or you're talking about something that you should not. But that is like 10 times lower than the other. This is just some examples. So in the top is the reference. A woman is sitting on a bench with a plate of food. This was feedback. Where the woman is sitting is not visible, so this annotator is a bit of a pain in the ass. And this is how they corrected it, right? So they just removed on a bench, essentially, right? Which goes along with their feedback. Some other example, a man riding on a motorcycle on a city street, and there is a man and a woman, not just a man. So here they're not telling you what was wrong. And then the correction. All right? So now we are back to our slide on policy gradient optimization, right? And now how can we actually put this information as some sort of a reward from the human teacher? Okay? So we're going to be using a little network to estimate this reward for us. Okay? And the idea is the following. So as you're doing your updates for the reinforcement learning, we need to do sampling, right? Because if you look at this thing, it has that expectation over there, right? And as you're training, your model is changing, okay? So as you're training, you're going to be seeing different captions for which maybe at some point this feedback doesn't apply anymore, right? And you need to be able to detect that as well. So we're going to be using like a little neural net that is going to take a new sampled caption, which is as part of your training, your feedback, both encoded with some LSTM, and then a phrase at a time. And it's going to be deciding whether this phrase is correct, given the feedback, wrong, given the feedback, or not relevant, given the feedback. Okay, and you're going to do that for each phrase. Okay, so that's going to tell you whether this feedback applies and whether it's correct or not. Okay. And there's a super simple way now to actually put it in your optimization, right? So we have the same reward function as whatever people are using, but we're going to make it a phrase level. So we're going to add an additional reward that's going to apply to each phrase individually, right? So it helps you solve the credit assignment, essentially, right? Because the text is describing where you're making the mistake. Okay, and you're going to do something super simple, right? So if the network says correct for this phrase, you're going to add 1 to your reward. If it's wrong, you're going to subtract 1. If it's not relevant, then there's no reward. Okay, so it's a very simple reward function. Okay, these are just some results. So the first line is just the normal maximum likelihood train model. So it's got some result. And this is the interesting part. So if you add to whatever data it was seeing, now on this subset of images, additionally corrected captions, which we get from this annotation around, you actually improve by quite a lot. I mean, 1 point. So this is if you're just training your normal reinforcement learning algorithm, let's say the one previously, you get this. So using 5 ground truth captions. And now we're giving it 1 caption less. Okay, so this model, our model has 1 caption less, but it has feedback. So together, it kind of sums to the same amount of information it's getting. Okay, and you are able to improve over all these results. And now we even have a human study that shows it's actually much better than it actually looks. But also take into account this was trained only on like 9,000 out of 120 COCO images. So I'm pretty sure there's a lot of room for further improvement. Let's skip this part. This is some results. Maximum likelihood. This is the reinforcement learning, the standard, the baseline. And this is the one with feedback. So now it gets the zoo correct. Tower with a clock. So it gets the preposition correct. And this is my favorite one. So a man is jumping into the air to catch a frisbee. Sounds good. A man is throwing a frisbee in a park. Sounds good. And then our model is not so good. A man is holding a frisbee in his mouth. So I guess there's some bias in the COCO dogs. So I think that's all my time. So I'm going to stop here. So if you have a 3-second question.
Thanks, Sanja. So we have time for questions.
Hi, about the first work, you use GAN to do image captioning. So I saw you use the Z, which is a conditional GAN on a Z.
Mm-hmm.
So what I've heard about conditional GAN is if you use Z, usually the GAN will just ignore the Z and just treat it as kind of encoder decoder. Do you have that problem? And how, if there is such a problem, how do you fix it? Thank you.
Yeah, that's a very good question. I haven't really investigated this, but I mean, it does look like it's generating very diverse captions, but probably there needs to be more study to actually show that they're as diverse as we wanted, or check the weights, I guess. Yeah, we haven't done that, but it's a very good point.
Other questions?
Also on the GAN work, did you check if the GAN output was well correlated with human judgments on the captions?
That's something that we're doing right now, yeah. So you can basically check whether they agree on the, yeah. That was one of the reviewers' comment, and I definitely agree. Yeah, it's in the process to do that. It's also, I have to say, the GAN didn't fully converge in the end, so it was like 60%, right? If one expect random if you really get it at the equilibrium. So, yeah.
Yeah, interesting work. Toward a question to the second work, you have to predict at one point if it's like if it's helpful or not helpful, or you don't know that really. And how
what? If what?
If this help from the teacher is really helping you, So how do you train it that it does it actually, that it works correctly?
What do you mean if it's helping you? So, oh, you mean like if they're saying something that's not,
Yeah, if
not
that's relevant.
if it's relevant?
Yeah, if
Oh.
it's relevant to your current prediction, current model
Oh,
state.
yeah. I mean, you have that ground truth.
So using not just
Yeah,
the
we're
language.
using that. Let me go back to
Okay.
this. Maybe here or this guy. But basically, you know that what's correct and what's not correct. And all the rest is not relevant under this. So that's your training data.
Okay, so you not just use the textual feedback, but really this pair.
At training time, we train the feedback network on this pair data, but then at test time, you're only using feedback.
No.
Yeah. This is just for training the feedback network. Yeah.
Oh, okay. Okay, thank you.
So in principle, you need a little bit of training data to be able to judge that, but from there on, it can only be just text.
So maybe I missed this and you already showed it. Is the feedback network then a good evaluation function as well?
What do you mean?
Like, can the feedback network tell mistakes in, let's say, premises or in incorrect captions that other systems are generating, not just?
No, so it's conditioned on the feedback. So it always needs that, right? So as soon as you give it some feedback information, then conditioned on that, it's gonna tell you whether something is correct or not.
Are there any more questions? Okay, so we are pushing the poster session back by 25 minutes. So it will start at 3. And now we have Anton as our next speaker. Anton is currently a professor in the School of Computer Science at the University of Adelaide. He is also the director of the Australian Centre for Visual Technologies and a program leader in the Data to Decision CRC. Anton has done some very interesting work in a variety of research areas within computer vision, including parameter estimation, machine learning, video surveillance, and interactive image-based modeling. Most relevant to this workshop is his recent work on visual question answering and his push towards methods which are capable of reasoning about the content of the image. Today, Anton is going to talk to us about VQA and why it's asking the wrong question. We are looking forward to hearing from you.
Thank you. Somehow I need to convince it to go all the way back. Okay, so yes, I'm Anton van den Hengel. I'm the director of the Australian Centre for Visual Technologies, and we've been doing work on VQA for quite a while now. I think it's a fantastic area, right? I'm really impressed. I think that it's, there's been this problem, I think, in computer vision for the last, 20 years, really, that we overreacted to the AI winter, and that we started just flat out rejecting any papers that started to question, even to move slightly towards AI questions. And it's not all that long ago where if you had a paper that had anything to do with language in it, that you'd be told to resubmit it to multimedia conferences or, just pretty much go somewhere else, right? And we as a field thus focused on a whole lot of, work identifying, spotting cows in fields and segmenting cars from roads and this sort of thing. And don't get me wrong, I've done more of that stuff than anybody, but I do really think that this VQA is a fantastic opportunity for the field to move forward and lighten up a bit and maybe challenge some questions that are a bit more interesting. I really think that it's a chance to take a step back towards hard AI. I think that the hard AI problem isn't going to be solved without vision. Humans are such visual animals that it would seem a great waste of an opportunity if we as a field don't take that step. So that's one of the characteristic images out of these data sets, and the corresponding question is wonderful, but the answer is even better. The methods are fantastic, right? The fact that we've been able to reach the point where you can ask a silly question about a silly image and get a sensible response is brilliant, right? It's a fantastic step forward. And originally when I asked this question, so this is, this is a answer that's out of one of our systems, right? It's a demo that's on the web. And I asked this question as a bit of a challenge for it, and I didn't expect it to get the right answer. And I think in retrospect it did. It nailed it, right? It had a better answer than I did. And so, these methods are fantastic at general image analysis. And the fact that you can ask the question afterwards, right? There's all of these visual problems, and pretty much every other problem in vision. You ask the question, you spend a year developing the method, and then you can apply it, right? This way, you get to develop your method and then ask the question and get an answer, right? It's a fantastic step forward, a real step towards AI. And the fact that you can that you don't have to train a soccer detector. Like you don't have to go, you don't spend 6 months going out collecting soccer images or other sports images and train both classes and all that sort of stuff. You can just turn up and ask it. It's a miracle, right? If you'd said that 2 years ago, 5 years ago, people would have said you're dreaming. So, and it does some real, so counting, right? Counting took humans a long time to learn. And there's still languages where there are. So the problem with counting is that the idea of number is abstract, right? There's no such thing as 2. Yeah, there's barely such a thing as 1, but there's certainly no such thing as 2, right? There's arguments until relatively recently about whether we should have 0, right? Whether 0 was evil and whether negative numbers even existed. And there are still languages where you have different number systems for different objects. And there are languages which stop at 4 or 5, right? After that, there's many. Counting is it's a complicated idea. And this thing, you can ask it how many horses are in the image, and it tells you how many horses are in the image. It's wonderful. Unfortunately, it doesn't really matter which image you ask it. It tells you the same number. But it's, it got it right the second time, yeah? I'm not convinced that had anything to do with the pixels, really. So I asked it how many unicorns were in the image. And it still, so I asked it that question because I thought that would be an example of where it couldn't possibly have learnt that out of the data set, right? So nobody could possibly have put in there. But of course, there could have been unicorns in the data set. I haven't looked. And, apart from missing a horn, those two things are pretty close to being unicorns, right? So I think actually, rather than being an example of failure, it's an example of success. So I asked it how many unicorns are in that image, and it got the same answer. So I think that, although we're asking, it's fantastic how far we've come, but there's this problem that I think that we're confounding the process of question answering with the process of developing the answer, right? So on the one hand, there's all of this, there's these fantastic data sets you guys are making which give you all of these examples of questions and answers, and they can tell you a lot about the way that people ask questions. I mean, the truth is that when people ask how many questions, the answer is 2, right? So that's not a disadvantage, that's an advantage. We've modeled something about humans, if not about images. But I think that trying to learn everything you can, everything you need to do general image analysis, right? The whole of computer vision, the field of computer vision has been trying to do general image analysis, high-level general image analysis for the last 30 years, and we're only halfway there. And you reckon this thing's going to learn to do it out of a couple of thousand question and answer examples? That's just not going to work, right? So I think we need to ask more interesting questions. So this is an example, right? This is a question I'm sure that you've all come up with the same answer. Irrespective of how much tennis you've played in your life, we've all come up with the same answer, which is neither of those answers, right? I like the idea that the tennis court is winning, but the fact is you need to understand something about tennis to be able to answer that question, right? It's relatively simple to determine. You look at which side of the net the ball's on and you can figure out what the answer is. Maybe that's too hard. Maybe it needs to be this is a simpler question, but again, these are not our results. These are from a web service, but it doesn't matter which one it is. They're all all of the methods will get the same result. It is neither no, yes, or like. So maybe we need something simpler to answer this question. You don't need to know anything about ski racing or what they're doing. All you have to do is know generally that there are these things where people compete trying to get somewhere quickest, right? And that means, that those numbers mean that they're engaged in some kind of race. And again, I like the idea that skiing is the real winner here, but the truth is it's 396 who's winning the winning. So, NLP QA tackles harder questions, right? They've been doing it for longer, and there are a bunch of advantages and disadvantages from what they do, but one of them, what was the monetary value of the Nobel Peace Prize in 1989? We're quite a long way from asking that question, right? They do it with a large set of documents, so it's closed world, or at least these examples come from a closed world thing, but those methods got 70% on those things, right? It's 3 gigabytes of images of text that got sent to these things. They have to read a hell of a lot to be able to find the answers. Watson won Jeopardy by answering William Wilkinson's account of the principalities of, I don't even know how to say that, Wallachia and Moldavia inspired this author's most famous novel, and the answer is Bram Stoker. There's an obvious image-based corollary or equivalent of that. Who wrote the book about this guy? The answers that our method provided were Michael, Bill, Queen, Big, and Baby. Quite a long way from Watson's answer, I think. And NLP aren't just feeding a whole bunch of questions and answers in and somehow hoping that their system is going to learn everything about the world on that basis. It doesn't matter what the architecture is, only that they're representing knowledge explicitly, right? They're doing a lot more, they're taking the knowledge that you need to answer these questions seriously. So we've been making some steps towards this. We haven't solved the problem, but what I like about where we're going is that we're taking some steps towards this AI version of the problem, right? That we're really trying to make a sensible step towards doing AI. This kind of fundamentally, VQA is our best opportunity, really, I think, in this field to make that step towards AI. So this one here is the questions, what's the dark green vegetable? And it's a bit hard to see on that image, but the dark green vegetable is cucumber. Our method gives you the right answer. A couple of very reasonable alternatives don't. But the real reason for that is that if you chop off the data set, then cucumber, so one of these approaches is that you only pick the few thousand most common answers in the data set. And that makes a lot of sense. Your performance figures go up, but you lose cucumber as an answer, right? It's not even an answer you can represent. So it's not that we're doing anything amazing. We're just looking at the rest of the answers. And these long-tailed, so we need to collectively move further into this tail, but of course we need to go past the tail as well. You need to be able to ask questions which are not in the data set, because the data set's never going to tell you everything that you need to know about the world. That process, so that one works by using an augmented memory. So the LSTM learns to drive a memory where it can store all of that information, right? So it still learns some of the information itself, but it has a much larger memory capacity because it has this augmented memory. Reasoning, I think, is critical, and that's where we should all be going, right? Trying to do actually explicit reasoning. This is a paper that's here where we're reasoning over graphs. And you know, the fact that we haven't been doing this before, it seems a bit crazy, right? You get the graph out of the graph of the language out of the NLP tools for free, and there's a lot of methods for getting graphs out of images. And yeah, so this is a really interesting question, I think. How many mammals are there in this image? It's a bit, oh, I've chopped some of the bird's head off, I'm afraid, but there's a cat, a dog, and at least the back half of a bird. To be able to answer that question, you need to know that birds aren't mammals, but that cats and dogs are. And so that means we've got to find that information somewhere. You can't write a mammal detector. And so you need to go out and find, you know, find the fact that, you know, this is a mammal and that's a, you know, so, and it turns out that that information is available, right? We don't need to try to train a CNN to understand the hierarchy of, you know, your Linnaean hierarchy of animals, right? You can get that out of, well, you can get it, kind of get it out of Wikipedia, but there are better sources of that as well. All right, but the tricky bit is once you've got that information, what can you do with it? So it's relatively easy to get, but much harder to use. So we got it out of Wikipedia, so you go and you grab the attributes out of the image, use that to search Wikipedia, and then you can feed those facts back into the language modeling process. That looks a bit like this, and it's a bit horrid, but it, you know, uses Dr. Vec to encode that information, and the LSTM learns to drive it, right? The LSTM learns to use information coming from Wikipedia as text in answering those questions. So in this one, it's asked a question about umbrellas, and it has this external information that it can leverage in answering the question, why do they have umbrellas, and comes up with the answer shade, where you're not going to get that if you don't have that other information. So, explicit reasoning. This is the stuff I'm most enthusiastic about at the moment, right? We need to separate the language from the reasoning. At the moment, pretty much what we're doing is just pushing the data into the, it's effectively just into the LSTM, holding our hands up and hoping that something sensible happens. And as far as I'm concerned, AI doesn't lie that way. People, you know, I'm saying that because there are people who are of the opinion that if we can just pump enough stuff into an LSTM or some sort of RNN, that it will memorize all of the information that there is to memorize. I'm not in that camp personally. And the other advantage of reasoning is that you can believe the answers much better if you're given an explicit reason. But it does mean that the reason has to relate to what's actually happened in the method, right? Otherwise it's just, well, you know, there are, well, anyway, there's a whole process about that, but I personally think that your reasons have to relate to what actually happened in the method that gave you the answer. So, and storing stuff explicitly means that you don't have to store it implicitly, which scales as far as I'm concerned. So, and why train a neural network to do something it's not good at? So the neural Turing machine paper particularly showed that you can strap LSTMs to other processes. So we did this work using a knowledge base. The knowledge base has these RDF tuples in it. There are a bunch of knowledge bases that you can get for free, and they're supposed to link to each other so you can chain through them. That in reality doesn't work very well, but you know, there's a whole field of semantic web people who are working on that. And the nice thing about using a DBMS to reference a knowledge base like this is that it does the inference for you. It will chain through, and it does, you know, people have been working on this for a long time, and it works very well. So in this work, you take the input image, you run your detectors over it, which we trained out of ImageNet, and you generate a bunch of detections, and then for each of those detections, you go into the relevant bit of DBpedia, and you can chain through that. So if you run your dog detector, you find a dog, you can, from that, go into Wikipedia. Wikipedia, which is where DBpedia is scraped from, will tell you dogs are four-legged omnivores, which are four-legged furry things, which are something or other, which are mammals, right? And you go through the same chain, and you can get from cats to mammals as well. And because you're doing this inference explicitly, you can count the number of mammals and report an answer. So, and that's the, so, you know, it's all done by chaining through the graph of things that are found in the image and then extended through these DBpedia concepts. One of the advantages of that, well, so the best thing is you can then get information which isn't in the image and isn't in your training set, right? So you can ask it, what are the relatives of this animal, and it will tell you. But obviously you can also get a reason, yeah, because it will tell you the chain that it went through. So I detected a dog. A dog is a mammal. I detected a cat, and a cat is a mammal, right? So it gives you an explicit reason about why it came up with that conclusion. All right, and the other, you know, so the next one that's actually here at this conference is an extension of that, which is based on the idea that we're actually, as a community, quite good at doing computer vision already, right? Some of us have been doing it for 20 years. And that the aspiration that we might teach these methods to perform the entirety of computer vision from a bunch of question, image, answer triplets is optimistic at best. You know, we need to learn how to drive these things. We need to learn how to drive the existing methods in order to be able to answer questions. If this is going to go beyond just being a novelty, right? So, yeah, we've already solved a lot of problems. We need to learn how to use those existing algorithms. And this is mainly the work of Chi and Peng, who are up the back there. And so here's an example. There's an image of a horse with a girl on it being led by a man in front of some stables. The question on the left is, what is the girl doing? The reasons that it's come up with are the information it's using, that is, the image contains the object of horse, the image contains the action of riding, the girl is on the horse, and the answer is riding a horse. The way that that works is we run a whole lot of algorithms over it that detect things that we need to know in order to answer these questions. And then the method learns to use the output of those algorithms in answering questions. So when you train the method, you run those algorithms over the training data, and the LSTM learns to use, or it's more general than that, the method learns to use that information. And I must admit, I was initially a bit skeptical about this attention stuff, but I was wrong. I think attention is critical. And part of what those two images there are showing you is that, so the bold words in the facts are the ones that it's paid more attention to, and the lighter areas in the image are the objects that it's paid more attention to. And you can see that the attention responds to the question, right? So different questions result in different images in the image being focused on, but they also result in different facts being selected and different parts of those facts inevitably being attended to. So there's a higher resolution version of it, well, a bigger version of it, so you can see it a bit more clearly. But you can see that the horse is being focused on and so on. And this is how it's done. You need to read the paper. I can't explain it all to you in the 1 minute and 10 seconds I have remaining, but it's effectively attention that's going on there, and it's co-attention. It's not just learning to attend to those things individually, it's doing them collectively. All right, so VQA, I think, has been fantastic. And again, I think it's a wonderful data set. VQA2 is an important step. I still think that, I mean, it's an important step particularly because it helps to isolate the language prior, but it doesn't go far enough. We need to go a lot further because at the moment, a lot of what's going on is just based on the fact that we're confounding the knowledge and the language. Yeah, we're using the same source for both, both different kinds of information that we need to use, and the two need to be separated if we're going to take the next step. So we need to move on to harder questions, and part of the problem I think that we have at the moment is that the questions don't mean anything, right? There's no purpose to them. You go and ask a bunch of Turkers to come up with a bunch of questions. They're not trying to achieve anything. They have no goal apart from making 15 cents, right? There's no, which is a big part of the reason that we have this evaluation problem. Because the VQA doesn't mean anything yet, right? And there's some fantastic stuff happening in robotics, particularly, where people are really grounding these, these ideas and starting to move towards, so I've been telling them that I want them to build a robot which can bring me a spoon, right? Bring me my blue socks, find the green Tupperware container in the fridge. They're real grounded concepts that need to be learned and reasoned about explicitly, right? So, and there's no evaluation problem with that because it's you're engaged in a process which has a goal. Whether or not you get your spoon back is really concrete form of evaluation, yeah? And we need to, look more at what the NLP community's been doing because they have some really good ideas, and they're ahead of us, right? They're asking and answering much tougher questions than we are, and it's a different problem, but it's so related that we really could stand to learn something. All right, thanks.
Any questions?
Here, actually. So very, 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 very impressive talk. I'm Joe from Arizona State University. We are actually looking into VQA for quite a while, and we are exactly working with an NLP person, like making this analogy between QA and VQA. One thing we typically observe is from QA, such as track data set, all these facts are not appearance, while what you detect from images are mainly just facts, appearance only. So I'm particularly interested, what's your opinion while you're making analogies between QA and VQA? And that's actually the question, because from the image, you don't get anything further from appearance only right now. So
I think that, yeah, indeed, absolutely. And I think there's an assumption that the next step is to, and we're as guilty of it as anyone, right? That you take your ImageNet detector and you find everything in the image and then you do your reasoning afterwards. But the truth is that the world, everything you need to know is never going to be an ImageNet. And you're going to have to know a lot more about what you're looking at than is ever going to be in ImageNet or DBpedia or whatever. There's a whole lot of information. There's a whole lot of information about the world that isn't written down and that you really have to learn out of images, right? So humans learn it by bumping into the walls and picking things up and dropping them on their feet and that sort of stuff, right? You have a relationship with dogs and cats that isn't written in Wikipedia, right? The information in Wikipedia about dogs doesn't tell you, that they want to be patted in one direction, not the other, and that they're, some of them will bite you and some of them won't. Yeah, there's all this other stuff that we need to know that's not actually written down anywhere, and it's got to come from somewhere. And I think learning that from images means that it's going to be applied to images, and that we need to find a much more sophisticated way to reason about the content of images. Yeah, I don't think that. So we in this community we tend to see reasoning as someone else's problem. And I think it's got to be much more grounded and image-based. Part of the reason I want to tell you all of that is because we're all going to wind up reviewing each other's papers, right? So, you know, make a bold step, write something crazy that's going to take, you know, that's going to impress everyone, and where the bold numbers are in all the wrong places. Yeah, I'd much rather be reviewing a whole lot of really interesting papers where the bold numbers are in all the wrong places, but it's a brilliant idea.
One more quick question.
So how do you see it, this like explicit reasoning? I mean, it's clear to me for some of these language things, but where do you see the explicit reasoning in the visual part?
I think that there's a bunch of methods already heading towards explicit reasoning, and that that model where you assume that everything, you know, that you can do all the detections and then reason is built into a lot of stuff that's happening already. Where I think it's going to go is that where I hope it's going to go is that with all of this enthusiasm for CNNs, we'll go beyond classes, and that we'll be able to represent the reality of the world, which is a continuous distribution of objects, right? And that we'll figure out how to reason about things that live in a continuous space, rather than, you know, if you want to put it into prologue or horn clauses or something, you've got to be able to say that it's one of these and it has these characteristics. And that doesn't really, you know, that's of limited use and heads us back to where the AI went wrong in the first place, right? You oversimplify and it doesn't generalize and doesn't have a practical impact. I think we need to really base reasoning on the reality of the world.
So with explicit, you don't mean discrete, continuous?
Yeah, continuous but explicit, right? I don't think that just putting it into a CNN and hoping. There's some great papers at the moment about learning relationships out of, you know, out of database knowledge bases, and about learning logical relationships, like just modeling a CNN, modeling a knowledge base using a CNN. Wonderful stuff happening. I don't think that's the way we need to go, right? We need to deal with explicit representations, but of continuous objects.
I'm just wondering how you're thinking this aspect of knowledge. In the examples you gave, I see at least a distinction between knowledge related to facts and knowledge related to physics. Like, the ball was not only on the wrong side, but like moving in one direction, and that's also, no, it's another form of knowledge you want to encode, and it's not clear to me how that relates to even a continuous version of facts reasoning for this.
Yeah, indeed, and I don't have the answers either, but I do know that there are a whole bunch of physicists who can't catch. Yeah, so we all did gravity at school, but it doesn't help you. Yeah, if you want to go and throw a ball, catch a frisbee, it's of very little use, right? And I think that a lot of it is really problem specific, but I don't have the answers, but all I've got is questions, I'm afraid.
All right, let's thank the speaker again. If you have more questions, we have a panel discussion at the end, which will be open to audience.